All right, so now we're going to look at question 3 from the quest. This one was one where we're given the graph of a derivative and asked to determine what's happening on the function that would produce such a derivative graph. And so it sort of builds ideas we've been discussing all semester long. The big key idea to keep in mind is, remember, the derivative represents the slope of the original function. So we're given some information in this paragraph, and we'll come back to that. But for now, we're just going to start looking at the first two questions. So we're asked, where would g, the original function, be increasing, decreasing, concave up, and concave down? And we're going to start with the increasing part. So for a function to be increasing, its slope would need to be positive. So that means we're looking for parts on the graph where g prime of x is greater than 0. And looking at the graph, there are sort of two places where I can see that happening. Right here between -6 and 0. And then again over here at 10 until the edge of my graph at 12. So for increasing, I'm going to have two intervals, one that goes from -6 to 0, and then I'm going to join it, that's a union sign, to one that goes from 10 to 12. And you can choose to include or exclude the endpoints. There's some debate out there in the math community about whether or not a 0 should be part of the increasing or decreasing intervals. I tend to go on the side of we don't include it, but either way is acceptable. Now, for the second question, we're asked, where is it decreasing? And so now we're looking for times when our slope is negative. So we want to find parts of the graph where g prime of x is less than 0. And again, there are two sections of the graph right here from -9 until we hit that 0 at -6. And then again, starting at 0 all the way until we get to 10. So both of those parts of the graph would be included in our decreasing interval. So we go -9 to -6, and that's going to be joined with 0 to 10. So we know where our graph should be increasing and where our graph should be decreasing. The next question deals with concavity. And I'm going to erase my markings on the graph, because now I'm being asked, all right, where is my graph going to be concave up? Well, concave up would imply that a function's rate of change is increasing. The function is either increasing or decreasing at an increasing rate. So we want places on the graph where technically the second derivative is greater than 0, which would be when the derivative graph has a positive slope, when it's increasing. So I want the portions of the graph where g prime of x is increasing. And now we have two sort of ideas up here in the initial paragraph that might help me with this, because we're told we have extrema at -1 and at 2. So I can see my graph is increasing all the way until I hit that extreme point at -1. Then it starts decreasing, and then it starts increasing again at the extreme point at x equals 2, all the way to the end. So both of those intervals are going to be where my original function g is concave up. So we would say from -9 until -1, and then join that with 2 to 12. And those would be the intervals in which my graph is concave up. We're also asked where it's concave down. So just as when the second derivative is positive, we have a function whose rate of change is increasing. If the second derivative is negative, our rate of change on the original function, our slope, we would have it sort of a decreasing rate. So we're looking for where g double prime is less than 0, which would be when g prime has a negative slope, so where it's decreasing. And so that's this sort of middle section right here. Oops. Between the two extreme points. So we would go from -1 to 2. So now using the information we just did on part A, we can answer part B as well. So part B is saying, find the X values where we have local mins, local maxes, and inflection points. I'm actually going to start with the inflection points. Okay, so inflection points should occur when we change concavity. So when our function goes from concave up to concave down, or from concave down to concave up. And right now on our graph, we can see two of those points really clearly. The two extremas on our derivative function. So I should have one concave up, or one point of inflection at -1, and the other one would be at 2. So there are 2 points of inflection. Now to get the local mins and maxes, we're going to be going back to that increasing, decreasing, because if we remember some things about the first derivative test, if our function changes from increasing to decreasing, we're going to have a sort of maximum point. If my function goes from decreasing to increasing, we're going to have a minimum point. So if I'm thinking about that in terms of the derivative, so I'm actually going to fix that a little. So we can do it with arrows. So increasing to decreasing. So if the function started off and was initially increasing, the derivative graph would be positive. At the maximum value, my derivative would be equal to 0 because it's a critical point. And then after that critical value, it would be the function would be decreasing. So my slope would be negative. So I'm looking, where does the graph change from positive to negative? Well, that happens at one point, right here at 0, at x equals 0, because on the left side, my derivative is positive, and on the right side, my derivative is negative. So I would have a local max at x equals 0, and I know that because g primes changes from positive to negative. Then if I go over to the local minimums, I'm looking where on the left side of my minimum value, my derivative would be negative because my function would be decreasing. At the minimum value, my slope should be 0 or undefined, but in this case, it's going to be 0. And then after that, my derivative would be positive because my function should be increasing again. There are 2 places where this occurs. So if we notice right here at -6, we change from negative to positive. So at x equals -6. And then again at 10, we go from negative, the derivative goes from negative to positive. And so our second minimum would be at 10. Once we have all this information, we want to use it to sketch our graph. And so that's sort of the last piece we do. Now, I know that I need my x-axis to go from -9 to 12. And I also know if I look up here that I'm told that we have a y-intercept at 0, 5. So I need to at least label that point on my y-axis. None of the other y-axis values matter, but I'm going to include a few, 1, 2, 3, 4, 5, 6, and I always give it a units. I need to go out to 12, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to go up to -10 over here. Don't assume that people know what you're counting by. Always make sure you label your axis with a number. You don't have to label all of them, but notice I sort of labeled the ends so that whoever's looking at my graph has a sense of where it's going. I know for sure I need a point at 0, 5, so I'm just going to draw that one in right off the bat. Now, I like to start by sort of drawing in what I call sketch lines. And so those sketch lines are going to be sort of the intervals, the sort of boundary lines where my graph switches from increasing to decreasing or where it switches concavity. So that I sort of have a sense of what's happening on my graph. And so I'm going to do it in gray. I'm going to make it sort of small. Okay. So I know that my function should be decreasing from -9 until 6. -6. So this is -9. That's sort of one boundary line. -876. So between those two values, my function is decreasing. And then I'm told that my function is, or I figured out that my function is increasing from -6 to 0. So I'm going to draw in another little dashed line, and I know that my graph should be increasing here. And then again, I can go over to the decreasing from 0 to 10. So 10's all the way over here. My function is decreasing. And then it ends by increasing again. So I have my sort of increasing and decreasing parts. The next piece that I like to draw in is sort of the concavity. And sometimes it's helpful to maybe do that in a slightly different color just so you don't get them mixed up. I'm going to do a slightly different shade gray. All right. So we're told that it's concave up from -9 until -1. So this line was -9, so I don't need to draw that in again, but all the way to -1. So that group, we should be concave up. And then from -1 to 2, our function is concave down. So I'm going to put a little frowny face there. And then the rest of the interval, my graph is concave up again. And now it's really just sort of a matter of connecting things. Now, since I know that this point right here, the 0, 5 needs to be on the graph, that might be a good place to start. I also know that 0 is my maximum. And I need to be concave down. So I might sort of even just draw in a little, ooh, I know this. And I need to be concave down basically until here. Right here at -1. And I need to be concave down on this side until 2, which is going to be another point of inflection. And now I'm switching to concave up. And I know I have a local minimum at -6, and it really doesn't matter sort of how I draw this, except I want it so that it's sort of a concave up shape where the low point comes here at -6, and then I'm sort of coming up from that side. And then again here, I should have a low point at 10, and I need my graph to be concave up, so I sort of want to go from my point of inflection and arch my graph so that I hit, a low point. You can see I sort of struggled a little bit to get that low point in there, but again, it's a sketch, so it doesn't need to be perfect. And then from there, I'm going to end the graph increasing. And I do not want it to auto make a line, but it likes to do that. So we'll go back in and sort of curve it a little more. And that's it. There's my function. Now, I was asked to not only label the x and y axis, but also the mins, the maxes, and the points of inflection. So I'm going to go through and do that. So this right here would be a point of inflection. And I'm fine if you abbreviate that POI, point of inflection. So we got another one right here. And then I have my local mins. So right here, actually, let's do a different color for our local mins. So let's do blue. So we got a local min, and we have another local min over here. And then last but not least, our y-intercept is also our local maximum. And there's my sketch. And, the purpose of those earlier questions was sort of to help me figure out how to best sketch. I'm using all this information to create that sketch that we see below. And your graph might look slightly different, but should have a local minimum at x equals -6, should have a point of inflection at x equals -1, must pass through the point 0, 5, and that would have been a local maximum. Point of inflection again at x equals 2, and a local min at x equals 10. You know, how far down that local min went, you know, that's sort of up to you, and how your sort of sketch appeared. Those particular values don't matter in this case. And hopefully that would help you tackle a question like this if we were to see it again on a future assessment.